Okay, guys, here we go. Today's lesson is on partial fractions. We're going to basically use partial fractions to help us integrate some rational functions that are really we wouldn't be able to integrate any other way. If our first choice, we would use some of the things that we've already done, like maybe we could add or subtract a constant in the numerator, something like that. That would be our first choice. If it's impossible, if it's a very complex rational function, remember rational functions are fractions with a polynomial on top and a polynomial on the bottom. So if it's quite, bulky, you're not going to be able to do one of our more simpler methods, so we're going to have to do partial fractions. These we added to the pre-calc curriculum just a few years ago so that we would practice this before you would have to do it, because really the most complex part of this integration is usually the partial fraction decomposition. The actual integration itself is much easier. It's just normal things that we would see. So really the hardest part, I think, for this, or at least the most time consuming, is the actual partial fraction decomposition. So let's kind of remind, now most of us probably worked on this. I mean, if you came from a different district or something different, maybe you didn't work with partial fractions, but if you were in one of the pre-AP classes here, you would have at least had a lesson on it. So let's take a look and see what we're going to do. The very first step, we want to divide the fraction out if it's improper. And we've actually talked about this technique before in a different context. Whether it's, so we compare the degree from the numerator and denominator. If the degree is the same or the numerator degree is higher, then we want to divide. So we would divide it out, and we would use long division to divide it out, and we would do the decomposition on the remainder. We would put the remainder over the divisor, and that's what we would do the partial fraction decomposition to. Our next step would be to take the denominators, and we're going to completely factor them. So we will go into linear or irreducible quadratics. That was a new vocab word last year, that irreducible quadratic thing. That would be something like x squared plus 1. If you had x squared plus 1 and you continue to factor it, you would go down into imaginaries. Okay, we want to factor until we get to the point where we would go into imaginaries. So that was irreducible quadratic. Let's see. So the next thing we would have to consider is if it's a linear factor that we get, we would put just an A over it, or B, whatever letter sequence we're in. If it's a quadratic factor, irreducible quadratic, we put like AX plus B over it. There's a pattern here, so if it's linear, I put a constant over it. If it's quadratic, I put a linear, like a binomial, over it. So that's something that we need to remember. If it's a repeated pattern, and that's what 3 and 4 are talking about, is repeated. So for example, let's say I had x squared plus 1. Well, we'll do the linear first. Let's say I had x plus 1. And let's say it was, let's ignore that part for now. Let's say it's to the third power. That's when I factored my denominator, I got x plus 1 to the third. When I did my, set up my fractions, I would have to put my x plus 1 to the first, x plus 1 to the second, x plus 1 to the third. I would have to repeat the factor as many, if this was to the fourth, I would have to have 4 different fractions for it. Same thing with quadratic. If it's a repeated factor, I have to do that same pattern, or it won't turn out correct in the end. That's the issue. It's a pattern issue. So if we were to add up all the little fractions that we created, we should get back to the main fraction we started with. It's really kind of a reverse of what we normally do. We're normally combining, adding things up. Here we're breaking it apart for integration purposes. It will help us integrate something that's quite difficult, make our integration much easier. Okay, questions on the concept so far? Okay, let's work on I think we just have one example. Oops, there we go. All right. So, let's move this. Let's take a look at our example. The first thing that we would do is we would kind of take a look at it and see, check the powers out, check our, to see if we have an improper. We don't, so we do not have to do long division. The next step, if you remember, is factoring the denominator. We want to factor it completely out. So this would be the same as 5x squared minus 3x plus 2 all over, see, we have x squared times x minus 2. Now once I get it set like that, I really stop doing the integral. I'm just going to pull out that fraction and I'm going to work with it. You know, we're not really talking about integration right now. We're just going to pull this fraction out and start messing with it. So we write it down in its factored form. Just that we don't factor the numerator. That's really, there's no sense in factoring the numerator. We set it up, and now we're going to write out our template. What fractions do we need to be working with? And I picked this one on purpose because this x squared usually throws students off. It is a repeated linear factor. It is not a quadratic. We would have to treat it the same if this were x cubed. If it were x cubed, we would have to do x squared, x cubed. Just because it says x squared does not mean that we treat it as a quadratic factor. We actually have to treat it as a repeated linear factor. That's why I picked this one. So my first, they're all linear. I don't have any quadratics in this. So my first fraction would be a over x and then plus b over x squared. That's taking care of this part of my denominator. Then my next fraction would be, c, would be c over x minus 2. And that's the setup of the fractions. Okay. What we do next is we're going to clear the fractions. I'm going to take this whole thing and I'm going to multiply it by just the denominator. Now I'm not multiplying by the number 1. I know that troubles some people, but it's an equation. I'm allowed to multiply by anything I want as long as I do the same on both sides. So I'm going to multiply by the original denominator all the way through so that I have no fractions left. And when I do that, I'm going to take this, multiply it by the first one, the first fraction here on this side, and I'm just left with 5x squared minus 3x plus 2. Okay. Then I take this and I multiply it by the second fraction. Notice how I already have an x here. So I'm left with a times x minus 2. Okay. The next one, b. As I multiply these two together, this term and this term, notice how the x squareds go away and I'm left with x minus 2 plus c. Again, I'm going to multiply this term times the original denominator and I'm left with x squared. Now, some of us from this point can just do the rest, set up our system in our head. You know, write it on and not have to distribute. I'm going to go ahead and distribute just to kind of remind you what it looks like. You don't have to do this next step if you remember it and can just read this. But I'm going to go ahead and distribute so it's a little clear to some of us who might have forgotten how to do this. So in my first term, I have the x squared minus 2x. So it's going to be my ax squared. And then I have, that's the first part, and then distribute. I have minus 2xa. So I'm going to put minus 2a. I'm going to put the x on the end, just a little easier when I collect. The next one is going to give us a b times x minus a 2b. And then the last one is plus cx squared. Okay. Now what I'm going to do is I'm going to set up my system of equations. And I usually put them in a little bracket just to kind of set them apart so that I know I can follow my work, what in the world I'm doing. And I normally don't mess with the original system that I set up here. I just do all my work around it. Now, what this technique does, it uses an SAT technique that you've probably practiced before, where we know that these quantities on the left and the right side are equal, so we match the coefficients and set them equal to each other. So here I have a coefficient of x squared is 5, so I'm going to set 5 equal to all of the coefficients on the right side that have x squares. So this one has an x squared, so A, done with that. Let's see, this one has an x squared, so plus c, and I'm done with that one. That's my first setup. Now, it is possible that our original numerator doesn't have an x squared term. If it doesn't have an x squared term, we would just set that equal to 0, because it would be 0x squared would be the term. All right, so let's collect the coefficients of the x's. So my negative 3 would equal, over here I have a negative 2a as a coefficient of an x, and I have a b as a coefficient of an x. And I'm done with the x's. The last one that I'm going to set up is the constant, and this numerator happens to have a constant. Sometimes they don't, and you would just put a 0 there. So I'm going to collect all the constants over here. That would be anything that doesn't have an x with it, which would just be our negative 2b. And that's the system that we're going to have to solve in order to be able to decompose the fractions. Okay, this one is fairly straightforward. This one's not a very difficult system because I already know I can find b. I mean, that's already set up for me. So divide both sides by negative 2 and I get b equals negative 1. So working backwards, I would put the negative 1 in for b and solve for a. And just for timing reasons, I think we're all probably pretty good at that. I'm hoping we're probably pretty good at the solving systems. We've been doing this for years, right? Years. So you should get an a. A would be 1. And c ends up being 4. Now it's possible that one of these, a, b, or c might turn out as a 0. That's actually kind of nice because that eliminates the entire fraction. We don't have to integrate that one. It just disappears. It's gone. All right, so we have our setup. Now let's work on integration. So I'm going to integrate. We have a is 1 over x, plus b is negative 1 over x squared, plus our c is 4 over x minus 2 dx. A much easier problem to integrate than the one that we started with. And normally it's pretty straightforward and simple integration. Normally it's not anything crazy. By the time you get to this point, it should be pretty well straightforward. So we know the integral of 1 over x is ln absolute value x. The second one we would do x to the negative 2, turn it into the reversal power rule, and we would get 1 over x. This last one really is kind of like a little baby u substitution, which when we first started u substitution, you would have had to write this all out, but by this time in our work, you probably can do this u substitution in your head. Probably, right? If we set u equal to x minus 2, then our du is just dx. We don't have any constant to mess with. And this turns in, it would be 1 over u du. So this would just turn to be 4 natural log x minus 2 plus c. I mean, it's possible that you could bring the 4 up into the argument here and make it to the 4th power. If you were working on a multiple choice question, they would probably write it that way. They'd probably bring the 4 up. But that's basically it. Questions on this integration technique? Yes, ma'am. This one? So I have an x squared that I have to deal with, and the x squared is, we treat it as a repeated factor. We do not treat it as a quadratic. So we have to do that special pattern where we do the x and then the x squared. If this had been x cubed, then I would have had an x and an x squared and an x cubed. I would have had 3 little fractions. Or x the fourth, I would just keep going. X the first. It's a pattern that they have found, the person who came up with this technique. That's how we have to do repeated factors. Okay, you're welcome. Anything else? All righty.